Okay, uh, students, yesterday we discussed, yeah, yesterday we discussed about key establishment, right? That is the third phase of key life cycle, isn't it? So, wherein we studied key hierarchies, where a simple three-level key hierarchy we discussed, where the master key will be at the top level, key encrypting keys at the middle level, and at the base there will be data keys, and these data keys are used to perform most of the cryptography computations, right? And these keys are also called as session keys. And after that, we also discussed scalable key hierarchies, where two approaches are followed for the key uh, for establishment. One is key translation, and next one is key dispatch, right? The next thing here is the next method which is used to perform key establishment is unique key per transaction scheme, or in short you can call it as UKPT. Okay, this UKPT scheme is another way of establishing a cryptographic key, and this establishes a new key each time that they are used. Okay, so it is UKPT is used to establish a cryptographic key, and it also establish a new key. Do you remember? It establishes a new key each time that they are used. So here, to perform any transaction, okay, to perform any transaction, a new key will be used. Okay, for each transaction a new key will be used. So this scheme is used, I mean the application of this scheme is at retail point of sales. If you look at this diagram, you can understand where this particular scheme is used. You might have visited many hypermarkets or food bazaar or big bazaar or such hypermarkets, where you if you purchase any product, that scanner will be there. While at the billing counter, the scanner will be there. It will scan the barcode, and it will find out the price assigned for the product that you have taken, and at the end you will pay the what whatever the price for the product, right, with the help of the transaction machine, isn't it? So at such point, you can see, 1 second. Okay, yeah. In such cases, you can see the swiper here. If you provide the card, the transaction card, either it may be credit or debit card, when you, with the help of that, you can purchase the product here, right? So this UKPT scheme adopts the method where it updates the key using a key derivation process after each use. So here, for each and every transaction that is performed in the shop or in the hypermarket, each and every time a new key has to be generated, and these keys are generated with the help of key derivation process, which we studied in the previous class. Okay, so here, as I said, UKPT scheme is used in retail point of sale terminals, where used by the merchants to verify pins and approve payment card transaction, as I said. Okay, so this is one application of UKPT scheme, and a question has been asked in your external on this topic. So the advantage of this scheme is that, see, if we follow this UKPT scheme, the advantages will be in this kind of scenario. I mean, if you use UKPT scheme, it will be better so that you can perform a secure transaction. See, terminals means this one, which we saw here. This terminal have limited security control, since they must be, because it is it costs less. That's why it can be deployed at the terminals, and at the terminal part, limited security controls will be provided. Okay, so it can be placed in insecure public environments, such as I said, stores and restaurant, Okay, and they are also portable so that they can be easily moved around, so it is easy for the what thieves to take it away, or it can be stolen easily. Okay, so the next advantage or the scenario where it is helpful is that transactions should be processed speedily to avoid delay. Okay, hence efficiency is important. So see, we can't wait for a longer time whenever we go to a mall or any restaurant or a shopping mall, right? We want everything to be done very fast, isn't it? So in such case also, this UKPT scheme helps in performing the transaction at a higher speed. So the third advantage is that terminals may be managed and operated by unskilled staff, hence full automation of the key establishment process is a necessity. See here, uh, see wherever, I mean in the hypermarket or the shopping mall, the staff who handle this terminal, who are placed at the terminals, who helps in what verify the PIN and approve the payment card transaction, that person may not be a skilled person. So the complete setup should be a automation one, so that the key established process should be done in a very secure manner. So these are all the different scenarios where you can use UKPT, that is unique key per transaction scheme. Okay. So there are many more examples given. Uh, so we'll see how the transaction happens between the merchant end where the terminal is present and at the card, the card server, or you can say the bank server. So here, consider, so let me directly go to the diagram. It will be easy for me to explain. Huh. See, this is the scheme where, this is the diagram where UKPT scheme is followed. Okay. This is followed at the what merchant, at the merchant side, the terminal is maintained, and at the host, that is bank or a card payment server. So whatever the transaction happens between these two entities, though that is shown in this figure. See, initially what happens, the terminal, here you can see the terminal. One second. This is terminal where you can see the key register is maintained. So this key register is essentially the running key that will be updated after every transaction. Okay. Next, here, one second. So I'm not able to know this. One second. Yes. Okay. So this terminal derives the transaction key. So as I said, terminal, at the terminal place also key register is maintained. At the host also key register will be maintained. So when a transaction has to be performed, then the terminal derives the transaction key. It derives the transaction key using the contents of the key register and the shared information that will be available to the host. So based on the data in the key register and the information that is shared between the host, using that transaction key is derived from the key register. Okay, that is the first thing. And then what happens? Then the terminal, see, this happens when you perform a transaction with the help of your card. Okay, bank card, payment card. Okay, then the terminal sends a request message to the host. You can see here, it sends a request message to the host. The transaction key is used to, this transaction key, the K, right? The K is used to compute a MAC on this request message. Okay. Then what happens at the host side? When the request is sent, the host derives the transaction key from the key register. Okay. And the host validates, what happens? The host validates the MAC on the request message. Okay. And then what happens? Once it validates the MAC on the request message, the host will send a response. So here the host will send a response message to the terminal. That means to the terminal. The transaction here also, the transaction key is used to compute the MAC on the response message. Okay. So once the response message is sent to the terminal by the host, then what happens? This terminal will validate the MAC on the response message, and the terminal updates the content in the key register. That means this data will be updated in the key register. So this is the steps that is followed when a transaction is performed between the terminal and the host. I mean, when we make a payment using a card, either it may be debit or the credit card, using which if we perform a transaction at the terminal, these are the steps that followed to perform the transaction. And do remember, this transaction follows UKPT scheme. Okay, do remember, for each transaction a separate key will be generated. Okay, and there is two more examples given here for which follows UKPT scheme. One is Rackle UKPT scheme, another one is derived UKPT scheme, and this derived UKPT scheme is used in Visa card. See, many bank issues Visa card, right? So that Visa card follows this derived UKPT scheme. Okay. So next, another way which is used to perform the key establishment is quantum key establishment. So it is a unique way of doing key establishment. So now we'll see this. Okay. So for this quantum key establishment, what is the motivation? See, actually, one motivation for this key establishment is that to provide or an attempt is made the establishment, see whatever what I can see, the schemes or the techniques that is explained in the previous slides, in that the establishment process will be a long, or the shared keys are involved, or the keys may be randomly generated, right? So those methods may take much time to perform the key establishment. Okay, so to overcome such problems or the such drawbacks of the previously discussed method, this key establishment method is followed. Okay, so we'll see how it works. So before going to this explanation, just see this diagram. See here, let me consider two parties are involved in the communication, Alice and Bob. Consider Alice is the sender and the Bob is the receiver. So if I am following quantum key establishment, then there should be a quantum channel between the sender and the receiver. Okay, before you communicate, there should be a quantum channel between sender and the receiver, as well as there should be a classical or the public channel, that is conventional channel, should also be set up between the sender and the user. Okay, this setup should be followed before we use quantum key establishment. Okay, so actually what problem arises here, I mean, in generally, that in a conventional communication channel, right, what happens, the simple way of establishing a symmetric key for the Alice to generate a key and then send it to Bob. Okay, if symmetric cryptography is followed, I mean, I'm considering an example where Alice and Bob are involved in the communication, and between them a conventional communication channel is set up. Okay, for the communication, consider what a simple way is followed to generate to establish a symmetric key for the Alice. Okay, and to generate a, I mean, the symmetric key is generated and then send it to the Bob. Okay, so how it is sent? It follows the conventional communication channel. So the problem with this approach is that the attacker could listen over the communication channel, and he may learn the key. See, if you know that in symmetric key cryptography, sender and receiver will use the same symmetric key, right? So if any simple method is followed, I mean, for the key establishment, then that key is sent to the Bob over the convention communication channel. So what happens? Attacker may listen to this communication channel, and he may learn the key whatever exchanged between the Alice and Bob. So, but the thing is, Alice and Bob will not be aware of this this attack. So what this attack? So they will continue with the communication, or they will start exchanging the data between Alice and Bob. But this creates a problem, right? So whatever the data exchange between Alice and Bob will be learned by the attacker itself, since he has the key that is shared between the Alice and Bob. So to overcome such problem, so quantum key establishment is used. Okay, so as I said, if we want to use quantum key establishment, then there should be a quantum channel. Okay, and this channel can be set up using a optical fiber network. So this quantum channel can be set up by an optical fiber network. Okay, so and then Alice and Bob, once this channel is set up, Alice and Bob must have the devices with them that is capable of sending and receiving information that is encoded as quantum states. See, for the implementation of this quantum establishment, special hardware devices are required. Okay, and these devices should be capable of sending and receiving information that can be read by these devices. That means these devices can read and send and receive the encoded bits. Okay, or you can say encoded quantum states, and this is called as qubits. See, I have given that explanation in this previous slide. Okay, so quantum channel need to be established, and special devices need to be deployed as Alice and Bob, where it will it will send or receive encoded data as quantum states, and these we call it as a qubits. You can see here, this is called as, sorry, one second. Once again, I got stuck in this slide. There is an issue with the PPT. As I said, devices need to be deployed at Alice and Bob, right? So here I have mentioned those points here. Okay, and this information is called as qubits with respect to quantum. Okay, and this is also known as, or it is also represented by the photons. So the data that is exchanged between Alice and the Bob, we can call it in the form of photons, and we call that as a qubits. Okay, so this quantum key establishment, one method is given, or an example is given, that is BB84, BB84 protocol, and this is also very important topic which they have asked in your previous exam. Okay, So here, as I said, let's consider this. Alice randomly generates a stream of qubits, that is nothing but the data, and sends this to the Bob, okay, in the as a stream of polarized photons to Bob. And what Bob will do at the Bob, I said the devices will be there, right? A specific device. So using which he will detect the photons either in the form of 0 or 1. So that can be done with the help of polarization detector. So that is depicted in this diagram. See here, BB84 protocol, where Alice and Bob are involved in the communication, where the quantum channel is also set up and the qubits are sent in the form of photons. You can see here 00110. In this way, the photons are transmitted between communication parties, and it will be in the form of photons, and these photons are detected by the polarized detector. Okay. So with this, as I said in this previous example, along with the quantum channel, there should be a public channel or conventional channel also, right, between Alice and the Bob. See, this conventional channel is required to prove the authenticated user. So Alice has to prove she is the authenticated user, and Bob also has to prove he is the authenticated user. Okay, so that is authenticated is done with the help of this conventional channel. Okay, so that is one thing you have to remember with respect to this protocol. So next, actually in practice, uh, how the quantum key establishment is used. So actually it has its own limitation. The first one is distance limitation, because actually in 1988, using this quantum key establishment, the distance covered is only 30 centimeter. And then by 2010, the distance covered by with this key establishment method is hardly 150 kilometers. So as I with respect to this, I can see it can cover only limited distance. The next limitation is data rates. So since data has to be, I mean, qubits or the photons has to be exchanged between Alice and the Bob over the quantum channel, there is a limit to the rate at which key material can be exchanged. So that is one more thing. Next is the cost. Here, the specific devices are involved. The hardware devices are involved, right? So that's why the cost of these devices is bit high. So the cost is an important factor when it comes to the quantum key establishment method. Okay, and also we need a conventional authentication as well. As I said in the previous slide, a conventional communication channel also has to be set up between Alice and Bob to prove their authentication, right, along with the quantum channel. So along the setup is itself time consuming. That's why along with the quantum channel, we need conventional communication channel also, right? So that's why this is one more disadvantage or the limitation when it comes to the quantum key establishment in practice. Fine. So that completes the key establishment phase. Okay. The next phase in key life cycle is key storage. So you know that secret keys need to be protected from exposure to the parties other than the intended owners, right? So if Alice and Bob are involved, then if they are using symmetric key cryptography, the symmetric key need to be shared between Alice and the Bob itself. It should not be shared with any other person, right? So that's why the keys should be stored very securely. Okay. So here we'll see how the keys are stored, how it is stored in the software as well as how it is stored in the hardware. Fine. So actually in many cases, we need not to we need not to generate or we need not to store this keys all the time. Based on the applications, we have to decide whether we have to store the keys or just immediately generate it and use it. So based on the applications, one has to decide it. Okay, so here there are some applications where you need not to store the keys. So in such case what you just generate them on the fly and then use it. Okay, so in such applications the keys are generated with the help of a deterministic key generator. Okay, using a deterministic key generator, key will be generated immediately and it will be used. So in such applications you need not to store the keys. Okay, so if you use a deterministic key generator, obviously it need a seed, right? So that is the initial value which is used to generate the pseudo random numbers. So here every time when you as I said, seed will be required, right? So and this seed to be consistently used each time when you need to generate the key. Okay, and this so every time if you need to use the seed, then you have to remember whenever you want to use a key. I mean, you have to remember the seed whenever you want to generate a key, but that is not, one second. Okay, so that is not the case, right? We can't remember the number or anything for a longer time, right? So that's why we can go for using a passphrase. So user generate a passphrase. See, passphrase is nothing but a statement. Like you can use it instead of password. You can use the statement as in the place of password. Okay, so that the user generate this passphrase. Okay, and this which the user has to remember this. Okay, and this passphrase, see, is if I give the password as what, PASS dollar dollar ORD or something like that. See, I mean enter it wrong when I want to log in the next time, right? So instead of using such password, if I use a phrase like what, I like dog, it's my pet animal, so that such fast phrase we can remember it for a longer time. Okay, so such fast phrase are used as seed for the deterministic generator that generates the key using which we can encrypt the key, or we can generate the key and you can use it. So that is about when you need not to store the key. And then the drawback of this method is that the security of the stored key is now dependent on the security of the seed that is used to generate the key encrypting key. So if passphrase is compromised, I mean, if any attacker comes to know about your passphrase, then the whole key generation process will get compromised, right? So that is one drawback with respect to this method. So what there are some other applications where we have to store the keys and use it later. So in such applications, we follow key storage in software. So how it can be done? You can embed the key into the software, right? So one common approach is to try hide the key somewhere in the software. So if you follow this method, there are two problems with this. One is the developer who designs the software will know where the keys are. Okay, and next one is assuming that hidden keys are specific to the okay. Assuming that the hidden keys are specific to the different versions of the software, an attacker who obtains two versions of the software could compare them. So the first thing is what? The developer who designs the software will be knowing the keys. He may, I mean, there may be a chance for the attacker to attack it and get the keys. Another one is what? See, for each software there will be different versions, right? So if we hide the keys in different version, the attacker, what he may do, he may obtain the two versions of the software, and he will compare and he may get the keys. That is one fundamental problem if you hide the keys in software. Next. Next is storing keys using cryptography. So how it is done? Encrypt it with yet another key. So as what name only, it explains what it is. So encrypt the key using another key. That is one thing, or generate it on the fly. The next one is store it in hardware and store it in component form. So this is the 4 different ways where you can store the keys using cryptography. So next is key storage in hardware. See, in the previous phase of key life cycle, we started hardware security model, right? Hardware security model where the master keys are placed. When we studied the key hierarchy, there we studied the top level keys need to be placed very securely. That's why those keys are placed in hardware security model. So the same concept followed here. The key storage is done in hardware, which is nothing but a hardware security models. So this is a very secure place where you can store the keys, and it provides the management functionality as well, and it is also known as tamper resistant devices. So this HSM is also called as tamper resistant devices. Okay, so this HSM can perform a huge number of cryptographic operations at high speed, and this HSM either be peripheral or can be incorporated into more general purpose device such as point of sale terminal. So this, I'll show you the picture of this. So these are the examples for HSM, that is hardware security models, where keys can be stored. And do remember, this HSM plays a very important role throughout the life cycle of a key. Either it may be key establishment, or it may be storage of key, or it may be in hierarchy, key hierarchy followed. So throughout the life cycle of a key, the HSM plays very important role since it can perform bulk cryptographic operation. Okay, and the keys which are stored in the HSM, that is hardware security model, are physically protected by the hardware. Okay, so how it is protected? See, if anyone attempts to penetrate this HSM, this device, consider if you want to extract a key from the device, then what happens? The tamper resistant circuitry is triggered, and the key is normally deleted from the HSM memory. So if any attacker tries to penetrate this HSM, what happens? There will be since it is a hardware device, there is a circuit which is called as tamper resistant circuit that is triggered, and the key which attacker wants to retrieve it will be deleted from the HSM's memory. Okay, so there are many tamper resistant devices. Those are micro switches, electronic mesh, resin, temperature detector, light sensitive diodes, moment or tilt detectors, voltage or current detectors, and security chips. So these are all the examples for tamper resistance devices or the circuit. Okay, so next there is an example given here, like key storage on an HSM. See, when we store the keys in HSM, one particular key is called as local master key. In short, you can call it as LMK, okay, that resides inside the HSM at all the times. So any other keys that need to be stored can either be stored inside the HSM, stored outside the HSM, encrypted using an LMK. So whatever the, this HSM is used to store the keys, right? So one key will be called as local master key, okay, which will be present all the time in HSM, which helps in storing other keys into it, either inside the HSM or outside the HSM by encrypting the key with the help of LMK. Okay. Advantage of using storing keys in HSM is that it is more efficient, and since keys we are placing keys in the HSM, right? So we need a backup for these keys. That is one more thing. There are key storage risk factors. You see that? See, as I said, the keys are stored in devices, right? So the risk may be pertaining to the devices on which we are storing the keys, as well as the environments within which the devices resides. So both the things will have a impact on the key storage. Okay, if you see this diagram, if you see this diagram, here the devices as well as environment is given. X-axis devices, y-axis environment. A devices says on which device you are saving or securing or storing these keys. That also plays very important role, and also where you are going to deploy these devices, the environment, that also plays a very important role. So here you can see this is divided as 4 zones: zone 1, zone 2, zone 3, and zone 4. In zone 1 you can see an uncontrolled environment is there. Okay, while moving towards second zone, partially controlled, and the last, the controlled zone is given, right? So devices may be the general purpose. As I said, HSM can be embedded in the general purpose device as well, right? So if we may use general purpose device to store the keys, or we may use dedicated or the specialized one. Okay, based on the zone, the risk factors increases. Okay, if you consider uncontrolled or the partially controlled and device used as general purpose, then the risk will be high here, right? So as you move to the second zone, there is a controlled environment where the risk will be less to store the keys in the devices if you follow dedicated or the specialized device. We'll see that. So as I said, environments range from uncontrolled to controlled, and also partially controlled. So here uncontrolled is that you can see the public environments like shops and the restaurants, right, where it is not possible to implement strict access control mechanism. The second one, as I said, partially controlled, like environments such as general offices and homes, where it is possible to implement basic access control system. For example, physical door key, such things. Next is the controlled environment, where high security offices and military installations are considered. As you know, there you can implement strong access control mechanisms. Okay. So next, with respect to devices, it ranges from general purpose, dedicated, and the specialized. See, in general purpose, what happens? General purpose devices running conventional operating system with their default inbuilt security controls. See, for example, laptop. Okay. So if you consider dedicated, then it offers some specialist security controls such as limited tamper resistance. For example, mobile phone. Okay. Specialized one, here main functionality is to provide security like HSM. Okay. So based on the device and the environment, the risk will be depend when you store the keys. Okay, so I said 4 zones, right? Zone 1, zone 2, zone 3, zone 4 with respect to this diagram. See, in zone 1, I already explained uncontrolled and the general purpose uncontrolled environment and general purpose device is used. So in zone 1, the risk factor will be high because less security is provided. In zone 2, as I said, controlled environment, right? So here, consider this example like a key stored in the software on a PC, okay, which provides excellent security if the PC is not networked and it is placed in a very secure room, right? So that is zone 2. And when it comes to zone 3, specialized devices need to be placed in uncontrolled, that is less secured environment. Like we place automated teller machines, right? That is ATM, right? So it is a specialized machine, but it is placed in a uncontrolled environment, right? So that is one thing. That is all about zone 3. About zone 4, the highest security zone is provided here as specialized device is used as well as controlled environment is uh, considered. So that's why the security provided zone 4 is higher compared to all other zones. So next is key backup, key archival, and key recovery. So these are three different key life cycle. As you know, key backup. So whenever we store a data, we'll be having a backup, right? So if you are using mobile phone, the images, videos, or whatever data that is present in your mobile phone, you would like to keep a backup of this, right? So you will be always uploading this data that is present in your cell phone to the cloud. In the same way, the cryptographic keys has to be uh, put in a backup. I mean, we should always have a backup for the keys. Okay, and to remember, it is always stored on the HSM so that it is easy to take the backup. Okay, so next is key archival. Key archival is another special type of backup which is necessary in situation where cryptographic keys may still be required in the period between their expiry and their destruction. So see, in our mailbox only we have archival, right? So in our message box also we have archival. So if anything is required, then you can look into the archival. I mean, the important things we will archive and keep it, right? In the same way here, the keys has to be archived whenever we may require it in future. Okay, then key recovery. So key recovery is the key management process where a key is recovered from the backup or an archive. So that is given in your syllabus. And one more thing with respect to key recovery is that it is a mandatory backup. So see, there may be a chance where we may lose the key, right? So it's like whatever key we created, that should have a backup. Okay, and this we call it as a key escrow. Okay, the idea behind of this key escrow is that if any data is encrypted, then a copy of the decryption key is stored by a trusted third party in such a way that with the appropriate legal authority, the decryption key can be obtained and used to recover the data. Okay, so here for this purpose, a key escrow is used. See, the key escrow we already studied in module 2 as well, where only few lines were given with respect to that, whereas here key escrow is related with the key recovery. Why the key escrow is required? See, if you encrypt any data and if you lose the decryption key, then it may happen that you may never retrieve that encrypted data, right? So in such cases, we should have a key escrow or key recovery. Fine. So next is key usage. Next phase of key life cycle is key usage. Here, um, see, we studied till now generation, establishment, and storage of cryptography keys in the key life cycle, right? So it is very important to have to specify the key usage. See, if a key is created, then we should specify what the usage of this. If a symmetric key is used, then the usage of that particular key should be mentioned. If a public key is created, then the usage of that particular key should be mentioned. Okay, so that is about the key usage. Here, under this we have key separation, where it says the principle of key separation is that cryptographic keys must only be used for their intended purpose. Okay, that means if any particular key is created, then that should be used only for the intended purpose. If it is created for the encryption, then the particular key should be used for the encryption. Or if a key is created for the decryption, then it should be used for the decryption purpose only. Okay, so now why we have to keep uh, keys separately, or need for separation? See, it's let's consider an example, like passwords, pins should not be stored anywhere in clear, right? Directly in a straight away, if I give password as ABC to my Gmail account, then that will not be directly stored as it is, right? What happens? These pins or passwords are often stored in encrypted form using a symmetric pin encrypting key. Okay, so in a direct form, it will not be stored. Okay, so this key should only ever be used to encrypt the pins only. See, if a symmetric encrypting key is created, then that should be used for encrypting pins itself. Okay, it should not be used for decrypting an encrypted pin. Okay, so in contrast, our normal symmetric data key. See, if I consider symmetric data key, which is used for both encryption and decryption, then these two keys also should not be interchanged, right? See, if somehow it is interchanged within HSM, then there will be serious problem. What happens? The first thing is that it may become possible to decrypt and reveal a pin. See, if I mistakenly used instead of encrypting the pin, if I use to decrypt a pin, then what happens? We may reveal the pin, right? So secondly, it's that it may not be possible to recover any normal data encrypted within the pin encrypting key. So this example says that you should what use key separately. That's why there is a need for separation. Okay. Next is enforcing key separation. See, enforcing key separation can be done in two ways: encrypting the key using a specified variant key, and the next one is embedding the key in a larger data block. So these two methods are used for key separation. So examples for this, for embedding the key in a larger data block, is employing redundancy. Second one is key blocks, and third one is public key certificates. So here I'll take up the key blocks because need with explanation. So here key blocks is a formatted data string that allows the keys to be represented along with other data relating to the key. That means what? This key blocks, see, uh, key blocks is nothing but a formatted data string, okay, that allows a key to be represented along with other data relating to the key. So for this, one example is given, that is ANSI TR31 key block. This is the block for this example key block. Here you can see the header. The header includes information that clarifies the purpose of the key. The header will give you the information about the purpose of the key, and optional header includes optional data such as expiry date of the key and such things. And key encrypted is using a suitable key for encrypting data. And the last one is authenticator. This authenticator is a MAC on the rest of the key block, which provides data origin, or you can see data integrity of the key block data. So here, why it is given, as I said, embedding the key in a larger data block. So whenever a key is embedded here, as per this example or this method, it should specify why it is used. That should be mentioned in the block itself. That is all about key blocks. And in employing redundancy, actually, here for employing redundancy, a method they have considered the example as DES, data encryption standard, where a data encryption standard key, which has the length of 56 bits, and but usually it is of 64-bit value, where the 8 spare bits that is present in the key that can be used for other purposes. And here actually the spare bits be used to provide error detection in the event that a DES key becomes corrupted. So that 8 bits is used for error detection if a key is corrupted. Okay. For this, key tagging was introduced in the DES key standard, where this allows these 8 spare bits to define the key usage. See, before the 8 bits spare bits were used for the error detection. After this, the standard was introduced is that key tagging, which defines, which explains this 8 spare bits for the key usage. Why the particular key is used. So when a key is presented in the command to an HSM, so as you know, the key will be stored in HSM, right? The tagging bits are checked by the HSM to ensure that the key is a valid key for the command that is being used for. So the cross check is done in the HSM with the help of tagging bits. That is about employing redundancy. And the last one is public key certificates. See, these are the type of key block used to provide assurance of purpose of public keys. So this public key certificates, see, you already studied the public key certificates in your networks, I guess. So a public key certificate often includes a field that defines the key usage. So whenever key is embedded anywhere, it should specify its usage. That's what this phase of key life cycle says. And I explained this key blocks already. And next topic is key change and key destruction.